So we computed P1 to be rho into P naught, and this is our second balance equation. This if again just working out, simply we get back P2 equals rho squared P naught, and since the same equation is repeating for all subsequent values of whatever be the value of n, n minus 1 and n plus 1, right, I can simply work this out in full glory. We will come back to this, Pn equals rho n into P naught. Right. So to calculate the value of P naught, we need to normalize, use the normalizing equation that all the probabilities Pi will add up to 1, and so we have sigma I equals rho in, or I equals 0 to infinity rho I P naught equals 1, and that only will work if rho is less than 1. Don't smile, I said this already. So if rho equals 1 it goes to infinity, rho greater than 1 it definitely goes to infinity, right. So that is a mathematical way of saying why this rho has to be less than 1. Intuitively people have asked me why should rho equal to 1, why will system become right unstable if rho becomes 1, and because number of because this is anyway, these are exponential variables, it is not that it is deterministic system, and I still haven't yet found that intuitive explanation why rho cannot be equal to 1. Mathematically we can say yes, if rho equal to 1 then what will happen if rho equals 1, actually what will be the system, if rho equals 1 what will happen for every arrival, no, yeah that is correct, but that is exponentially distributed, right. So if lambda equals mu equals 1, right, and we look at our distribution, look at that same Markov chain where all the values go to 1, right. So what will happen is it will be simply 1 over infinity, right. See what will happen is we will see why that goes to, why it becomes an unstable system. See your mu equals lambda, right. So basically P naught equals P1, so all the probabilities become equal.
That will always remain in one state only, that will, because one is coming and one is going.
So we are saying that the system state, no, that is not correct either, it will be unstable, it will actually go towards infinity, it will be, so you have P1 P naught equals P1 all the way up to P infinity, right. So if I apply sigma Pi equals 1, what will happen, P naught will be 1 over infinity, so it will become 0, so the probability of being in any state is 0. So the system will never stay in a given state, so it keeps on moving to the next state, next state, next state, and so on.
But it is like mathematically we are saying, but if we take it otherwise, by saying that lambda equal to mu, that means the number of processes which are coming, same are being taken out.
Only thing, the arrival times are different.
But it is exponential distributed, no?
See the times of actual arrival, even though it is 1 and 1, the actual times of arrival is random, and because of that again the system keeps on building up and it ends up being in an, will be an infinite state system, or the Q size will be infinite in that particular system. Okay, so that's, so we derive that P naught equals 1 minus rho. Okay, so what does this mean now? So now let us look at what should we do with all these probabilities that you have calculated. So for that we wanted to define some metrics for the Q, right. So the Q's performance metrics. So 1, so in terms of the customer there is a delay, right, we said average delay, we will say average packet delay, and this is represented by the total time spent in the system. Okay, so total time from arriving to the system to departure from the system, entire time spent in the system is 1. We will use this variable to be R, so the expected value will be E of R to follow the book's notation. So R stands for response time, right, this is the response time. So what is this E of R, so that we need to complete. Then we also would want to know what is the waiting time in the system, because the service time for a particular customer we know it is 1 over mu, because mu packets per second or mu customers per second are being serviced, so the average service time is 1 over mu, right. So therefore each customer we know it is 1 over mu, we are sometimes interested in the waiting time of a particular system. So in some cases what will happen is, in some systems the waiting time will be less for one system compared to the other, but the total time will be different, right. So we have to look at sometimes waiting time also. So this is the average waiting time. That the book uses W, we hope, yeah, right. So this is the time spent in the system before start of service. So waiting time is simply the time spent before start of service, and we will call this to be W. So I need to know what is the average waiting time, and that average
Before start of service, because the queue can packet can also try and maybe go back.
this is a simple open ended queue, there is no going back to this queue, you enter, you leave, right.
Okay.
So it's an open system, it's not a closed loop system. We will come to queue networks where you actually go back, the one that we saw last time where you actually go back, right. So that will be a closed network system. So this is simply an open system, customer arrives and leaves, that is all. So then we need to know what the average waiting time is. So that is one more thing that we can try to figure out, and then another metric. So this relates to buffer size. So again, looking at the system, you would like to know what is the average occupancy, average buffer occupancy, right. Because if you are deciding a router and then you are putting in gigabyte of memory, you find that most of the time only about a few kilobytes or megabytes is being used. So why invest in a gigabyte of memory, because memory is expensive in routers, right, and also power consuming. So you sometimes want to know what is the average number of customers in the system, average number of customers in the queue, right. Number of customers in the system equals the ones waiting plus the ones being serviced, or the average number of customers simply waiting in the buffer, right. That is also some things we should look at. Okay. So this is the number of customers in the system, including the ones being serviced. I am saying ones because if I have multi server system, then I can have more than one customer being currently serviced, right. And unfortunately the variable for that is used is n, which is appearing all over the place, but we know when I say E of n, you know what I am talking about, okay. And the number of customers, this is now only in the queue. This is just the buffer occupancy. Okay. So what is the average number of customers simply sitting in the queue, that it is called NQ. Okay. So the first two are from the customer's perspective, what is the waiting time. The customer does not care how many customers are there in a particular queue, right, or whether the queue is fully occupied or less half occupied and so on, except in the cases where sometimes you go to a queue, right, multiple queues are there, each counter having its own queue and all of them are giving the same service, and they say pick any one, you will always pick the shortest one. Only at that time the customer can visually see what is the current queue length, and based on that you can make some decision, right. But the queue length is more of a system level parameter or metric. System wants to know how many customers are waiting, right, and because based on that the manager has to come in and add more tellers or make this guy go faster, right, process this thing faster so they can have the queue size to be less. Then there is also one more, which is the utilization of the server, right. So what is the server utilization? So server utilization is simply the fraction of time that the server is being utilized. That is also metric, because if I am going to put in 5 people, right, for the job in a bank, and I find that half the time or most of the, on average only 2 people are actually servicing customers, so I am utilization is 2 out of 5. So I am paying 5 people's salary and getting 2 people's worth of work, so which means I can remove some customers and or clients, or remove some servers and put them in some other branch where there is heavier demand. Okay, so these are some of the metrics, and then here it is not just total time. This EFR is simply the expected time. Sometimes you also want to know the distribution of response time and what is it, the variance in response time. All those things are there. Okay, so now that we know what we want to measure, right, so let us see how we can use these PIs. Ultimately all I have computed so far is the PIs. Okay, so how can I use the PIs to determine any one of those metrics? Does any of those metrics look calculatable based on the PI values that we know? the number of customers, right. At every state I know in state n there are n customers in the system. So therefore I can first compute E of n. So I know the probability of being in state n, and I know that this is a reward that we saw, right, in the last tutorial. You calculated for, if you know Pi, then the reward of that state is whatever, $10, $1 and so on, right. And this is n going from 0 to infinity. Again rho should be less than 1. So what does this work out to? So this is again similar to the geometric variable derivation, so we will not go through all that, but simply rho by 1 minus rho. So this is the average number of customers in the system. So we have found something, one metric, right. So well, good thing is it's closed form. So we, okay. Now what else can I derive? How do I go forward? Can we derive the E of n cube, number of customers waiting?
Total number minus two, which are processed.
So I could derive that too, right.
It won't be this minus 1.
It won't be minus 1?
I'm asking. Which
So if I am in state n with 5 customers, what does it mean? There are 4 waiting and 1 being serviced, right, because I am 1. So it is always n minus 1, so into Pn, right, except that n goes from 1 to infinity, because n equals 0 there is nobody waiting. So your summation goes from 1 to infinity, which you can derive like, right. So we can go through the derivation for this one too, yeah, which will turn out to be rho squared by 1 minus rho. Yes, you are saying something? This after simple derivation you will get, okay. So this is something also that we can derive. Okay, now what do we do? Now what is the utilization of the system? How or what fraction of time is the server being utilized?
Except when the state is 0.
Yeah, so except when the state is 0
Or 1.
yeah, oh even one server is being utilized, right. So it is basically 1 minus P naught is what you are saying, right. P naught is the state the system is being idle, no customers is P naught, therefore 1 minus P naught is and P naught is by the way 1 minus rho, right. So this is simply rho, I would have simply said rho because lambda by mu, right, fraction of packets arriving to the fraction of packets leaving is simply, but you can derive it this way too, right, it is not always, so utilization of the system is simply rho. Now we want to calculate delay. So how on earth we are going to get a delay? So far there is nothing that gives us delay for a particular packet, right. So for that we need to take a sidetrack and look at something called Little's law. Okay. So you look at any system as a black box and let the system have sub blocks also inside. So this is a system that is handling some processing, whether it's cache requests or customers arriving. So into this black box I have customers arriving at rate lambda. Okay, so lambda is the rate of something entered. This is not even Poisson, nothing. It's simply plain lambda, right? This is simply arrivals per second. That's all. Okay. Then I can measure the total time spent in the system. Right. This is time spent or average time spent. So I enter the system. I spend some amount of time, right, which is we will call that T, average time spent in the system equals T. Okay, so this is arrivals per unit, this is time average time spent in the system in the same T units. Okay, and then I will simply count. I am not sure how to show, but let us say, right, the total number of customers, right, at a given point in time. So we will do that. Okay. It's the average number of customers. Okay. So call this N. So N is simply number of arrivals into the time spent, average time spent in the system. The average number of customers is simply arrivals into average time spent in the system, which you can do with a simple integration equation and show that this is true, but we will not worry about that, right. So all I need to know is, if I know the arrival rate and if I know the average time spent in the system, I can compute the average number of customers in this black box, or vice versa. Any one of these, any two of these I have, I can calculate the third one, and this is true of even sub blocks. So if the sub blocks, right, also I can apply the same thing. So for any subsystem inside the system, even for that, if I say this is N1, right, this is N1 lambda 1 T1. So for all sub blocks also this relationship holds. So in general any black box where customers are being handled, this rule will apply. So if this is N2 equals, remember we saw that when I have in that previous example, right, where you CPU you go to one of those queues. So even though individual queues you can apply Little's law to find out. If I know 2 or 3 parameters for the small device queue, I can again calculate the third parameter for each of those queues, or you can look at the entire system and calculate the overall time spent in the system, right. So for even the CPU queue alone, so this is applicable to any subpart of the system, I can use it as needed. Okay. So this Little's law is what will now help us move forward after that E of NQ. No, there is no assumption on the distribution at all. Yeah. When looking at the mean arrival, mean time stayed, mean time spent in the system to the mean number of customers in the system.
Sir, one option is the total number of processes entering should be equal to total number of processes which are coming out.
Oh, okay. Even see that there is okay, where okay, fine, yeah, I'll have to draw that, and yeah, so there is it is yeah, so nobody is staying in the system, true. Okay, so with that Little's law, now I can start equating. So E of n, right, is the total number of customers in the system, that is now equated to total arrivals to this q into the average response time. The average total time spent in the system is r, right. So, E of n equals lambda into E of r, and E of nq equals lambda into E of. So, this is nq is w, right. So, nq is the number of customers in the queue and w is the time spent in the queue. So, therefore, E of nq equals lambda E of w. E of nq, so this is the subsystem that we talked about, right. So, if I look at my queue,
How you calculated the number of customers in
oh how, oh okay, let me just draw this picture for the sake of completion. So, this is E of n and then E of r, this is lambda. This little part of the system where excluding the server is where your E of nq and E of w apply, right. To both systems the packets arriving are at rate lambda, right, and there is no packet dropped in the system. Lambda is effective, all the packets enter this queue and therefore nq and EW can be equated, and likewise E of n and E of r can be equated. Questions?
How you got that, sir? Pn. Why
So,
you
Pn is the probability of being in state n. So, when I am in state n, how many customers are waiting for service? State n means I have 5 customers in the system, one is being serviced, right. So, the 4 guys are waiting for service.
This will be only true for this case when we have only one server.
Yes, correct. When we go to, we can do the same thing, it will be n equals m to infinity, right, and it will be n minus the number of if it is if it is less than m, there will be nobody waiting. If I have 5 queues, 5 servers, then when the system is in state 0, 1, 2, 3, 4, 5, there will be no waiting at all. Only when I go to 6th, when the state goes to 6, will I start having waiting in the queue. So, it will be simply n minus m into Pn, that is all, and n will go from 0 to infinity, or sorry 1 to infinity, right, or rather n plus m, m plus 1.
So, sir, when we say it is mu, the service
Sorry,
time
time,
when we say service time distribution is mu, what do we actually mean? That
when I say the service time
distribution
is exponential, yeah. So, that again if you, so this is our mu, it means that your the service time distribution would be given by your f of t, right. This is what our definition is, where there is, remember that if you draw the f of t, is that correct. So, whenever you find a system where you are measuring the cumulative your CDF, and if it is having this particular, if it fits this pattern, then you say that it is exponential.
that I understood. Physically, I am asking means.
Physically, that is what it is. So,
In real sense, how do you say ki service time distribution?
so you will have to do a reverse fitting. So, you sit and measure, right. You measure the service times for all the customers in the system, and you take the probabilities of, right, the time for each of those, the service time being 1 unit, being 2 units, 3 units, and so on, and then you try to see if it fits this particular distribution. If it does, then you say it is exponential.
Okay, so you plot it like this number of customers.
Yeah, you have to do, you essentially you are trying to fit your set of sample points to some known distribution, right. If you are measuring the service times, right, and let us say that you have, this is the f of t that you are trying to do, or f of whatever it is, right? Okay, service time. So, we are saying what is the probability that the service time will be 1 unit, some, let us say that this is just a discrete set of values, it is not, right. If you get something like this, right, there are only 5 possible values, it is not exactly a continuous distribution, it is, right, there are only 5 possible values, everything else goes to 0, right. So, this is your distribution, you cannot say this is exponential because this is what you observed from say million samples, you go to 2 million samples, maybe this will change, right, you got the wrong set. So, that is basically looking at the service times and seeing if it maps to this nice convenient distribution, because if it does, you get these nice properties of memoryless and so on, but in real life most likely it will not, but you just make the assumption. We did that assumption when we tried to do, for example, packet queues, right. Packet lengths are never exponential. First of all, your packet lengths are also only discrete set, it is not, it will go from 0 to infinity, it is not going to be the case, right, whereas here anything greater than 0 will is its defined form, right. But we are simply making that assumption just for the sake of convenience. You are saying my ATM multiplexer is an MM1 queue, and that is, then you just use that assumption to get some closed form results for what the delay will be.
the ith state, and expected time for all the packets to be serviced in that state.
Okay.
Probability of the packet coming in ith state, entering
Okay.
in ith state, equal to the steady state probability of the ith state
Okay.
into the expected time in that ith state, service time for end customers in that ith state.
Okay, so that is, you are saying it is n by mu, n minus, no, n by mu. If you are in state n, the waiting time is n by mu, right, because mu is the average, 1 hour mu is the average service time. So it is n by mu into probability, steady state probability. Okay. Okay, we will check it out, right, because we can calculate that. Okay, so we will try both ways and see if it gives us the same equation. I have not tried that, but we can try. Okay. So now E of n, or E of n we know, right, E of n is rho by 1 minus rho for rho less than n, then E of r is now 1 over lambda into E of n. So 1 over lambda, and this is no, lambda by mu 1 minus. So what do we have? So this is an equation that you should never be able to forget, right? So expected time is simply 1 over mu minus lambda. That is why again rho should be less than lambda, otherwise it does not make sense. If rho equals lambda, again here you find that it E of r goes to infinity, which is again correct if rho, right, again mathematically speaking. Intuitively speaking, think about it, but mathematically if rho equals mu, you will end up lambda equals rho equals 1, you will end up with infinite delay. Okay. So in fact if you look at the response time distribution itself as a random variable, I will just state that the CDF of r itself, f of r, is actually exponential. Which means the response time is exponentially distributed with parameter mu into 1 minus rho. That is the interpretation of that. I will just leave it at that for now, let us not go any further along that, but this main thing is this, the delay is, the average delay is 1 over mu minus lambda. Okay. So now you know there is another relationship that exists between E of r and E of w, right. So the total response time is simply the waiting time plus the average service time for this particular packet, right. So therefore I can calculate E of w as which we can sort of massage this and actually end up with one over mu into rho by 1 minus rho. we can also have derived, we could also have derived EFW from EFNQ. Right, EFNQ we said was rho squared by 1 minus rho. We could have applied the same thing, basically 1 over lambda rho squared by 1 minus rho. So if I take out one rho from there, rho by lambda is nothing but 1 over mu. There is an extra lambdas. If you take out one lambda, one rho, you will still have rho by 1 minus rho, and rho by lambda is nothing but 1 over mu. So we can derive it this way. Okay. So in this form, if you look at it, E of W is 1 over rho, 1 over mu, sorry, right, into this particular fraction. This is one way of looking at 1 over mu, it's easier to remember, but to actually interpret this, I would rather use this one, 1 over mu into 1 by 1 minus rho. So what this says is 1 over mu is the average service time, right, per packet. So the average service time, so the system response time depends, is inversely proportional to your, or actually no, it is, if it is 1 minus rho, then yeah, higher the utilization, higher the delay, it is directly proportional to your utilization. But this 1 over mu is a multiplicative factor that appears for both EFR and EFW. So when you are trying to design systems, always make sure that the 1 over mu factor goes to as small as possible, because everything is proportional to 1 over mu. So smaller your service time, which means faster your link, right, faster your server, then your overall response time is going to be much better, will be lower. Okay, so now that we have seen all these equations, unless we see some numbers, probably will not be fun, right. So we will take one example. Right, there is my, okay, I will just start off by simply saying arrival is 125 packets per second, right. And the average service time is 2 milliseconds. So assume that this is an M1 queue, right, this is a packet queue. So if you remember the internals of a router will have queues, right, and for each queue packets are arriving, and let us pretend that the packets are arriving at some Poisson, right, that is given by lambda, and average service time, which is 2 milliseconds. So nobody said that the average service time for packet is exponential, which is never the case, but if somebody says what is the average delay spent by a packet in this particular queue, we will say, oh well, because it is not deterministic, I presume that it is Poisson, exponentially distributed, and then I will try to get some closed form solutions. Okay, so mu is simply 1 over 2 500 packets per second, right. So now I can say E of R is 1 over 375 So what is E of R? .66 milliseconds. It is good that it is greater than mean service time, right, otherwise something went wrong with the formula. So therefore E of W is simply minus 2, that is 0.66, and so on, right. So E of n is rho by 1 minus rho. So technically we always calculate rho first, but sometimes we ignore the rho and both states. But anyway, so what is here? So here rho is 0.25, 1 by 4. Yeah, we can do lambda here also. Yeah. In this case, there are different ways to calculate that. So this is simply 0.25 by 0.75, therefore that is 1 by 3. And so on. So now we get a hang of numbers. Now we have the purpose of actually going through all this calculation, right. So either we do not learn about Markov chain, simply use the formulae directly, but it is good to know how we got these so that we can use this for analyzing other systems, right. So these are systems that have been analyzed over several decades ago, but this is the way that you got some of these closed form equations. Okay. In fact, there is some other ways of computing. Yeah. Okay, there is one more example here. Questions? There is one example here that is interesting. So you should look at this. There is a long list of formulae, right. I am only giving you some of the expressions. So if you go back and look at this box 31.1 on page 525 of. So usually he summarizes for every Q type. This is a good reference. So you certainly want to just know what the results are. Don't care about how to derive it, right. This is a good way to find it. So we only know, for example, the mean delay, right, but what if I want to know the 90th percentile of delay, right. So we will have to go back to our statistics definitions, but here, so we will just give you the result for the qth percentile of response time or packet delay. So people are familiar with percentiles, right, after having written, right. So if you want to find out, because sometimes the mean delay alone does not tell me much, I would like to know, right, like some sort of worst case delay to see what is going to happen, right, and that gives me some, if I am trying to design some systems, right, for example buffering, I want to know what the average, what the worst case delay is, so buffers have to be proportional to delay, then I try to get some of these estimates. So in this case, if if q equals 50, what do you get? What is q equals 50, 50th percentile? 50th percentile is what? 50th percentile is?
50th percentile, okay.
Is a mean.
Median.
Median.
50th percentile would be, yeah, sorry. So that will be into log 2, yeah, natural log 2. Yeah, so sorry, your mean is E of R. So. So if you want q equals 90, right, so what is the 90th percentile of delay, so which means that 90% of the times, right, the delay values will fall below this. So that is simply natural log of 100 by 10. So natural log of 10, natural log of 10 is 2.3. So that is a fairly large number, right. So your delay can have wide variation, so in this particular case. So if in this previous example if the mean was 2.66, then the 90th percentile is 2.3 times that, right, which is fairly large. In the previous example, what is 2.3 into 2.66? Use my own calculator. Six 6.1. So if the application designer requires to know the worst case delay also, right, then you can get that again here, and again these, because you are making an assumption that it is exponential distribution time for the service and so on, sometimes that is not, so it just gives you an idea of how much will be the worst case delay, right. I can put 95 also and see what is that going to be, and so on. So there are other expressions also here, I just want you to look at them. Okay, now if I say if rho equals 0.9, okay, and idealistically I only have about 1000 buffers or a capacity for 1000 packets in the system total. So what is the probability that I will exceed 1000 packets? What is the probability the queue occupancy will be more than 1000 packets? So either you can just try to compute this, right. So what do I want? I want to try to, let's say that some n is what I am looking at, right. So probability of there being greater than equal to n customers. Okay, now since we used n before, some k customers, right. So that is simply summation of all probabilities pk, no, Pn since we used n, and going from k to infinity, right. And then what is this? This is rho to the n into 1 minus rho.
So why are we taking it like this? Why are we not taking it like Tn Q?
This is the probability of, this is simply the probability of that being. We are trying to find out E of NQ. Now E of NQ is only the average number of customers in the system. Here I am trying to find out the probability that will be more than n customers or k customers in the system.
So shouldn't we calculate like that? Probability of like 1000 customers means it is in that state is like
Yes, that's the probability of there being more than 1000, 1001, 1002 and so on, right?
Yes.
That's what you are trying to compute here.
Be like that sigma put n is equal to 1000 into that probability
Yeah, I know,
of being
just
that
making
state.
that as k and then k, from k to infinity, anything more than k is what I am interested in, right? Yeah, more than 1000, greater than or equal to k customers. So what does it converge to? So we can also compute that. So in some cases it is easy to find this out, right? And if you have forgotten the high school derivation, you should go back and try it out, right? Okay. Now we will do MMM in the next 5 minutes, right? Now that done MM1, MMM is very similar. And so what if I have m servers, right? Again infinite capacity. So what will be the Markov chain and what will be the balance equations and what will be the final solution. So has m servers, everything else is the same as before. Okay. So now the states again go from 0 through m minus m, 1 m and so on. So this transition is still at the rate lambda because there is only, right. So there is one queue being serviced by several clients, there is only one single queue and there are several servers. Okay. Now the return service rate, so if there is only one customer, one server active, right. So what we are assuming is okay, so there are m servers each of capacity mu and they are n identical servers. Okay, we will make sure that, and there is one common shared queue. So many times when we go and see queues being arranged, right, sometimes they put separate queues, the service is the same, you can say any teller, right. Sometimes they have a common queue, sometimes they have individual queues, and we can look at which of these actually is better, right. So if they are done queuing theory, they have to figure out that one of these two is better, and right, and because if you go to SBF, there is a single queue, right. It's they use a token system is a single queue and you just get serviced by the next available server that is waiting. Okay, so when I have one server active, the return rate is mu. We have two servers active, the return rate is 2 mu, and this is again similar to that lambda 1 plus lambda 2, same, right. If either of those two servers can finish and then you will go down to the next lower state. So this is m minus then subsequently after m you only have m servers active, so it will be always b and so on. So this is a generalized birth death process where lambda 1 lambda 2, right.
Means like for example from 2 to 1, why can it only come to 1 if there are 2 servers? They
Because
can
you are
finish.
looking at, as long as either of those 2 servers finishes, you come down to state 1.
But they can simultaneously also finish. It can come to 0 also.
That assume that there is a, it's a 2-step process, right. That is where your memoryless thing again comes in. So you go from 2 to okay.
But understood. Why that is like this only?
Okay.
Yeah.
Because this is the effective rate of transitioning from 2 servers to, from 2 customers being handled to 1 customer being handled, okay.
But it can be 0 also, no, sir?
From M to 2 also can be the same.
From
Say suppose you have 2 customers in this thing, what is the rate at which I can go to 0 customers?
It can be
It will still be
also.
2 mu.
If both of them.
we will work it out. Okay, we look at the exponential and then work it out. See, what you are looking at is you are looking at 2 independent processes, right, with rate mu, and then you are trying to find out the min of those 2 whenever one of those 2 events occurs, right, the same lambda 1 lambda 2. So the rate for that, you are looking at the minimum time for either of those 2 to finish is what I am looking at, right, the rate for that. That is again exponential with rate mu plus mu equals 2 mu, that is what it is coming to, okay, right. Because as long as either of those 2 finishes, you go to, remember we did the derivation, right, even if they are equal, right, x1 equals x2 or x1 is so on, so that is taken care of by that definition. So conceptually yes, they can go at the same time, right, but the rate of transition is still, it is still an exponential process with rate 2 mu. So that is where sometimes you try to our sort of on a day-to-day basis, yes, I can go instantaneously, both of those can be, but if you look at the probabilistic process that is defining it, it is an exponential process with rate 2 lambda, and that is what we are trying to capture. So that it's okay for now, we will just use that, and then it takes some time to see what the process, look at it from the probability process, not as a specific instant that is taking place at a given point in time.